Hi, everybody. So now we're going to talk about a sort of an extra topic, which is an application of the ideas from Euler's theorem to a practical situation, which is the problem of what's called public key cryptography. And this is actually used in web browsers and e-commerce applications and lots of other situations nowadays all the time. So let's start with a little discussion of what is public key cryptography? And maybe before we talk about what is public key cryptography, we should talk about what's cryptography. And so the problem that we have is we have two people, here's A and here's B, and they want to talk to each other. And they want their communications to be secure so that an eavesdropper cannot hear what's going on between them and capture that information. And in traditional or private key cryptography, the way this could be done is that A and B could agree in advance on some kind of system for encrypting their communications by, let's say they might agree on a cipher where A is going to translate A's to 1 and B's to 2 and C's to 3, and B knows that that's the system that A is going to use. Now, obviously, that's a very simple system, but one could generalize that. But the key obstacle that A and B face is that to set up a cryptographic system like this, it seems like they would have to somehow meet, or at least first get together and agree on this system. And one of the problems that the World Wide Web and other security applications raised is, how can you have a secure communication channel between two people who have never met? So like, I want to buy something from Amazon, and I can't sort of have a secret meeting with Amazon where we agree on how we're going to communicate. So I have to be able to talk to Amazon secretly without anybody else knowing it, but without any agreement in advance. And what public key cryptography does is make that possible by separating the problem of encryption and decryption. So in other words, let's suppose that A and B want to talk to each other. And so I want to send a message to A. I want to send a message from A to B. And let's suppose that I have a special box which I can open, which I can put my message in. But once I lock that box, only B knows how to open it. So in other words, A has a method for converting something. I can encrypt a message using publicly available information. But once I do that, only B can read it. So this is really rather strange. I'm A, I can take my message, I can use some public information that B has given me, I can convert my message into secret code, and then the only person who can undo that is B. Even I can't undo it. If I were to somehow forget what my message had in it, I'd be out of luck. And that's what's called public key cryptography. And it's public key because the method for putting things into code is public, but the method for taking it out of code is secret. And you can reverse that. It could be the other way around. That is to say, the message for taking things out of code could be public, and the message for putting them in could be secret. But the two are separate, and knowledge of one doesn't give you knowledge of the other. So I'm going to describe this method, which was published by Rivest, Shamir, and Edelman. That's where the name RSA comes from, in the 70s, but which was actually discovered by the British cryptographic team at Bletchley Park during World War II, but they kept it secret. So it didn't become publicly known until the 70s, and it's therefore known by the RSA algorithm. And to make RSA work, we're going to choose two primes. Typically, these are very large prime numbers, but in my example that I'm going to work through, we're going to use the primes 7 and 13. So there's not going to be a lot of security here. And the first thing we need to know for the RSA algorithm is we need to know that the Euler function evaluated on a product of two prime numbers is p minus 1 times q minus 1. So remember that phi of pq is the number of elements in the group U of PQ, which is the number of residue classes mod PQ that are not divisible by either P or Q. So why is this true? Well, let's think about this for a moment. Let's do a very quick example. Let's suppose P was 5 and Q was 7. So we want to look at the integers mod 35. So there's 35 of them. I'm not going to write them all out, but just to give you the idea, I'm going to write out the first few. And we want to figure out how many of these are not divisible by 5 or 7. So we would cancel out the ones divisible by 5. And how many of those are there? Well, there are 35 residue classes, and 7 of them are multiples of 5. Right? 5 times 0, 5 times 1, 5 times 2, 5 times 3, 5 times 4, 5 times 5, and 5 times 6. And then 5 times 7 would take me back to 35 again. So we have 7 multiples of 5. And then how many multiples of 7 do we have? We have 5 multiples of 7. Namely, 0 times 7, 1 times 7, 2 times 7, 3 times 7, and 4 times 7. So if we throw those out, we have 35 residue classes. We throw out 7 multiples of 5. And we throw out 5 multiples of 7. But we have to be a little bit careful because we've double counted 0. 0 counts as both a multiple of 5 and a multiple of 7. So we don't really have 7 multiples of 5. We have 7 multiples of 5 and 5 multiples of 7. But if we're counting how many actual numbers there are, which are multiples of 5 or 7, we've counted 0 twice. So we better add one of those zeros back in so we haven't counted it twice. And if you look at this, this is 35 minus 7 minus 5 plus 1, which is the same as 7 minus 1 times 5 minus 1. In other words, it's 6 times 4 is 24. So more generally, we can count the following. Given PQ, we count 0 once, and then we count 1 times P, 2 times P, out to Q minus 1 times P. This is Q minus 1 multiples of P. And then we have 1 times Q out to P minus 1 times Q. This is P minus 1 multiples of Q. How do we know there's nothing in common between those? Well, if you're divisible by both P and Q, then you'd be divisible by PQ, and that would mean that you would be congruent to 0 mod PQ. And we're only looking at the numbers up from 0 up to PQ minus 1. So the only multiple of both P and Q which can fit in that interval is 0. So the total number of multiples of P or Q is 1 for 0, plus Q minus 1 for P, plus P minus 1 for Q, which is Q plus P minus 1. And the things which aren't multiples are PQ, that's the total number, minus P plus Q minus 1, which is PQ minus P minus Q plus 1, or P minus 1, Q minus 1. And so we've shown that the number of residue classes mod PQ, which are relatively prime to both P and Q, is in fact P minus 1 times Q minus 1. So let's file that away for the moment. So the next step in working out how the RSA algorithm works is to pick a decryption key D, which is relatively prime to M. And you just pick any number that you like. So I'm using as long as it's relatively prime to M. So I'm using, remember, P is 7, Q is 13. So M is 6 times 12, which is 72. It's P minus 1 times Q minus 1. So I have to pick a number which has no factor in common with 72. So I picked 5. 5 is a perfectly good number. And then I have to solve the equation. This is all going to seem very magical at the end, so bear with me. Solve the equation DE is congruent to 1 mod M. Not mod PQ, but mod P minus 1 Q minus 1. So I need to solve the equation DE is congruent to 1 mod 72. Now, normally you would do this by Euclid's algorithm, which is pretty efficient, but I'm going to sort of cheat and just tell you that 29 works, because 5 times 29 is 145, which is 2 times 72 plus 1. So D times E is in fact congruent to 1 mod 72. Now here's the thing that we're going to use. Remember, the goal is to have a decryption key and an encryption key. And they need to be such that knowing one doesn't tell you the other. And D and E are going to play that role. And the thing that's going to make this whole thing work is that if you take X, any number mod N, so any residue class, now it has to be relatively prime to N, which means not divisible by P or Q. In practice, P and Q are going to be huge numbers, and the chance that you're going to pick a number at random which is divisible by P and Q is going to be 0. In our case, we have to be a little bit careful because we're working with smaller numbers. But so we pick an X which is not divisible by P or Q, and notice that if you take X and you raise it to the dth power mod N, and then you raise it to the eth power mod N, that's the same thing as raising it to the deth power mod N. But DE is 1 plus a multiple of M. Because remember, DE was congruent to 1 mod M. And M, in this case, is phi of N. It's Euler's phi function of N. And so this is congruent to X times X to the phi of M, N, to the K. But this X to the phi of N is 1 by Euler's theorem, so this is congruent to X mod N. In other words, if you first raise something to the dth power mod N, and then raise it to the eth power mod N, because of Euler's theorem, you get back where you started from, mod N. So here's how you do the RSA algorithm. You publish, so that everyone can see them, the numbers E and N. So in our case, we would publish N equals 91, E equals 29. And we would keep secret D, which is 5, and M, which is 72. Now, just to be really clear, even better, you're never going to need M again. So you should probably destroy all copies of M. You really just need N and E to be public, and D you keep secret. And E is called the encryption key or the public key, and D is called the decryption key or the private key. Now, how do you use this? So I want to send a message. Remember, the goal is to send a message from A to B. A knows N and 29, or maybe more generally, N and the encryption key, and B knows the decryption key and also N. And what is a message? Well, a message is a number. Somehow you have to convert your message to a number. There are lots of ways to do this. For instance, you could just take your message, convert it, type it up on a computer, and use ASCII and break it up into blocks so that it's numbers. Or you could make every A be a 1, and you could split your message up into blocks. Somehow you convert your message to a number. And now, let's say that my secret message is 19. So I want to send 19 to B, and I don't want anybody to know what it says. So I look up the encryption key 29, and I compute 19 to the 29 mod n. So here I'm using only information that I know, namely n, which is 91, and the encryption key, which is 29. And it turns out that this works out to be 80 mod 91. Never mind how I did that calculation. Let's assume that you have a computer that can do that quickly. And so I send 80 to B. Well, B takes his decryption key, or her decryption key, which is 5, and computes the 5th power of my secret message mod 91, and magically, because of what we saw earlier, because of Euler's theorem, gets back my secret message 19. So I was able to send my secret message using the publicly available information, and the recipient was able to decrypt the information using only his privately available information. Now, why is this secure? In other words, what's so great about this? Well, the key point is that if you know E and N, to figure out the decryption key D, you need to know M, which is P minus 1 times Q minus 1, and then you need to solve DE congruent to 1 mod M. So it's easy to solve DE congruent to 1 mod M if you know M. But you don't know M. You don't know P minus 1 times Q minus 1. You only know N, which is PQ. So given PQ, can you find M? And what's amazing is that as far as anybody knows, the only way to figure out M is to factor the number n and find its prime factors p and q, and then compute p minus 1 times q minus 1. So at the heart of the security of the RSA algorithm is the question, if you have a number n, which is a product of two large prime numbers, can you find those prime numbers? Can you factor n? And as far as we know, this is impractical if n is large. And by impractical, I mean that if the two primes have 300 digits, let's say, so that n is a 600-digit number, which is a product of two 300-digit primes, the time which it would take, using the best algorithms and the best computers in the world, to find p and q is on the order of centuries. And so to all practical purposes, it's impossible to do, and therefore this message is secure. And it's true that early on in the RSA business, people thought maybe 50 or 80 or even 100-digit primes might be good enough to keep security. Now maybe you need 200 or 300 digits, but we've kind of reached a wall there. And there are some theoretical estimates as to how hard it is to factor. And they suggest we're not going to be able to do this in any reasonable time. But it's not known for sure. And it is possible, although very unlikely, that there is a way to do these factorizations more quickly. It's also possible that quantum computers may become practical and will render this method insecure, but also that at the present moment is science fiction. So if you choose your primes large enough and you make your n large enough, then the RSA algorithm, as far as anybody knows, is essentially unbreakable, and for that reason, it's widely used. I just wanted to now make one comment. There's one question here which I think needs to be answered, and we'll talk about that in another video, which is, to make this work, let's say that n is on the order of 600 digits. Well, what do you have to do? So D, which is or E, for example, E and D, they might also be residue classes on the order of 600 digits. And you need to, if x is your number and you need to compute x to the e mod n, raising x to a 600-digit number requires some thought. It's certainly not the case that you can do x times x times x times x times x times x, because to do that 10 to the 600 times is going to require many, many, many multiples of the age of the universe. So for this to be practical at all, there has to be a practical way to compute powers mod n, even when the power and the n and the base are all very large. And there is a way to do that, and it's a clever technique called repeated squaring, and we'll talk about that in another video.